In September of 1846, a German astronomer named Johann Gottfried Galle pointed his telescope at a specific patch of sky and found something extraordinary. Not because he stumbled upon it by accident, but because a French mathematician named Urbain Le Verrier had told him exactly where to look. Le Verrier had never observed this object himself. He had never even used a telescope to search for it. Instead, he had calculated its existence using nothing but mathematics and the misbehavior of another planet. That planet was Uranus, discovered 65 years earlier by William Herschel, and it had a problem. Uranus was not where it was supposed to be. After decades of careful observation, astronomers had plotted its orbit with increasing precision, and they kept noticing something wrong. The planet was drifting. Not dramatically, but enough to be measurable. Sometimes it moved slightly faster than predicted, other times slightly slower. Its path through the sky deviated from the calculations by small but undeniable amounts. Now, there were two possible explanations for this. Either Newton's law of universal gravitation was wrong, which seemed unlikely given how well it worked everywhere else, or something invisible was pulling on Uranus. Le Verrier chose to believe the latter. He sat down with pen and paper and began working backwards. If an unseen planet was perturbing Uranus, he could use those perturbations to calculate where that planet must be. The math was extraordinarily complex, involving differential equations and celestial mechanics that would make most people weep, but Le Verrier pushed through. After months of calculations, he arrived at a prediction. He sent his results to Galle at the Berlin Observatory, and within hours of receiving the letter, Galle found Neptune. It was less than 1 degree away from Le Verrier's predicted position. The discovery was hailed as one of the greatest triumphs of mathematical astronomy. An entire planet, invisible to the naked eye, found not by searching the sky but by following the math. It proved that Newton's laws were even more powerful than anyone had imagined. If you understood gravity well enough, invisible things would reveal themselves. Now, more than a century and a half later, history appears to be repeating itself. Once again, astronomers are noticing something strange in the outer reaches of the solar system. Once again, the math points to an invisible planet. And once again, the skeptics are asking whether we're seeing a real pattern or just wishful thinking. But before we get to the modern search, we need to understand the principle that made Neptune's discovery possible. It's called perturbation theory, and it's based on a simple idea. Every object with mass exerts a gravitational pull on every other object with mass. When you have a planet orbiting the Sun, its path would be a perfect ellipse if nothing else existed in the universe. But other planets do exist, and each one tugs on all the others. Jupiter pulls on Saturn. Saturn pulls on Uranus. Earth pulls on Mars. These pulls are tiny compared to the Sun's gravity, but over time they add up. They cause planets to speed up or slow down in their orbits. They change orbital shapes and orientations. These changes are called perturbations, and if you can measure them precisely enough, you can work backwards to figure out what's causing them. This is exactly what Le Verrier did with Neptune. He treated Uranus's orbital deviations as a puzzle where the missing piece was an unknown planet, and by solving for the mass, distance, and position of that planet, he could make the puzzle fit together. The same technique was tried again in the late 19th and early 20th centuries, when astronomers noticed that even after accounting for Neptune, there were still small, unexplained wobbles in the orbits of Uranus and Neptune. This led to the search for Planet X, which culminated in Clyde Tombaugh's discovery of Pluto in 1930. Except Pluto was far too small to cause the perturbations astronomers had observed. It turned out those perturbations were probably just measurement errors, artifacts of imprecise observations with 19th century equipment. When Voyager 2 flew past Neptune in 1989 and refined measurements of its mass, the supposed orbital anomalies vanished. There was no Planet X, after all, at least not in the form people had imagined. But that doesn't mean there's nothing else out there. Beyond Neptune lies a vast region known as the Kuiper Belt, a disk-shaped collection of icy bodies left over from the formation of the solar system. These objects are sometimes called trans-Neptunian objects, or TNOs for short, and they come in all sizes. Some are just a few kilometers across. Others, like Pluto, are large enough to be considered dwarf planets. The Kuiper Belt extends from about 30 astronomical units from the Sun. That's 30 times the distance from the Earth to the Sun, out to roughly 50 astronomical units. Beyond that lies the scattered disk, where objects have been flung into more eccentric and tilted orbits, probably due to gravitational interactions with Neptune billions of years ago. And beyond that, even farther out, lies the inner edge of the Oort cloud, a hypothetical sphere of icy bodies that marks the true boundary of the solar system. We've been discovering TNOs at an accelerating rate since the 1990s. As telescope technology improved and systematic surveys began scanning the outer solar system, hundreds and then thousands of these objects were cataloged. Most of them follow relatively predictable orbits. They're cold, distant, and unremarkable. But a few of them are anything but ordinary. In November 2003, astronomers Mike Brown, Chad Trujillo, and David Rabinowitz discovered an object that would come to be known as Sedna. At the time of its discovery, Sedna was about 90 astronomical units from the Sun, 3 times farther than Neptune. But that wasn't even close to its maximum distance. Sedna's orbit is extraordinarily elongated. At its closest approach to the Sun, it comes within 76 astronomical units. At its farthest point, it travels out to nearly 940 astronomical units. It takes approximately 11,000 years to complete one orbit. To put that in perspective, the last time Sedna was at this point in its orbit, humans were just figuring out agriculture. The next time it returns, we'll probably have colonized Mars or gone extinct, possibly both. What makes Sedna so puzzling is not just its extreme orbit, but the fact that it exists at all. Objects in the scattered disk, like Eris or Makemake, have eccentric orbits because Neptune kicked them outward billions of years ago. But Sedna never gets close enough to Neptune for that explanation to work. Even at its closest approach, it's still twice as far from the Sun as Neptune. So what put Sedna on such a bizarre trajectory? For years, Sedna was considered a fascinating anomaly, an outlier that defied easy explanation. Maybe it formed elsewhere and was captured by the Sun's gravity. Maybe a passing star perturbed its orbit when the solar system was young and embedded in a star cluster. Maybe it was evidence of a distant, undiscovered planet. Or maybe it was just a fluke, one weird object in a solar system full of weird objects. But then we found more. In 2012, Trujillo and Scott Shepard discovered another object with a Sedna-like orbit, designated 2012 VP-113, and nicknamed Biden after the then vice president. VP-113's orbit is similarly detached from Neptune's influence. Its perihelion, the closest point to the Sun, is about 80 astronomical units, and its aphelion, the farthest point, extends beyond 400 astronomical units. Once again, no known mechanism could easily explain why this object was where it was. Two extreme objects might still be a coincidence, but they hinted at something deeper. If Sedna and VP-113 were part of a larger population of distant TNOs, and if those objects shared similar orbital characteristics, that would be very difficult to explain through random chance. And as more surveys scanned the outer solar system, more of these objects turned up. By 2014, astronomers had identified a handful of TNOs with perihelia beyond 50 astronomical units and semi-major axes. That's the average distance from the Sun, greater than 150 astronomical units. When Trujillo and Shepard published a paper analyzing these objects, they noticed something odd. The arguments of perihelion for these distant TNOs were clustered. They weren't randomly distributed across all possible values. Instead, they seemed to be aligned in a similar direction. Now, to understand why this matters, we need a brief detour into orbital mechanics. Every orbit has several key parameters that describe its size, shape, and orientation in space. The semi-major axis tells you the average distance from the exact Sun. The eccentricity tells you how elongated the orbit is. A circular orbit has an eccentricity of 0, while a highly stretched orbit approaches an eccentricity of 1. Then there's the inclination, which measures how tilted the orbit is relative to the plane of the solar system. Most planets have low inclinations because they all formed from the same rotating disk of gas and dust. But TNOs can have inclinations of tens of degrees or more, especially if they've been scattered by Neptune. The argument of perihelion is a bit more abstract. It describes where in the orbit the object makes its closest approach to the Sun, measured as an angle. If you imagine looking down at the solar system from above, the argument of perihelion tells you the direction the object is heading when it reaches perihelion. For a population of objects with random orbits, you'd expect their arguments of perihelion to be evenly distributed. Some objects would reach perihelion pointing north, others south, others east or west. There should be no preferred direction. But that's not what Trujillo and Shepard found. The distant TNOs they studied had arguments of perihelion that clustered near 0 degrees. They were all reaching their closest approach to the Sun while heading in roughly the same direction. The odds of this happening by chance were low, but not impossibly low. With only a handful of objects, it could still be a statistical fluke. Trujillo and Shepard suggested that a distant planet, perhaps several Earth masses, could be shepherding these TNOs into aligned orbits through repeated gravitational interactions over billions of years. The idea was intriguing, but the evidence was thin. That changed in January 2016, when two Caltech astronomers, Konstantin Batygin and Mike Brown, published a paper in the Astronomical Journal that sent shockwaves through the planetary science community. The paper was titled Evidence for a Distant Giant Planet in the Solar System, and it made a bold claim. Not only did Batygin and Brown argue that a ninth planet existed, they predicted its properties with startling specificity. According to their calculations, this planet had a mass between 5 and 10 times that of Earth, making it similar in size to a smaller ice giant. It orbited the Sun at an average distance of about 400 to 800 astronomical units, with an orbital period of 10,000 to 20,000 years. Its orbit was highly elliptical, with an eccentricity around 0.6. And, critically, its orbit was inclined relative to the plane of the solar system by about 30 degrees, and oriented in such a way that it was nearly anti-aligned with the clustered TNOs. In other words, when Planet 9 was near perihelion, the TNOs were near aphelion, and vice versa. Bataille and Brown hadn't just noticed the same clustering pattern that Trujillo and Shepard had observed. They had run detailed computer simulations to test whether that clustering could be explained by a distant planet, and the answer was a resounding yes. But only if that planet had very specific properties. Too small, and it wouldn't produce enough gravitational influence. Too close, and it would disrupt the inner solar system. Too far, and its effects would be too weak. The simulations pointed to a narrow range of parameters that fit the observations almost perfectly. The paper included analysis of 6 TNOs with well-characterized orbits, all with semi-major axes greater than 250 astronomical units and perihelia greater than 30 astronomical units. These objects weren't just clustered in their arguments of perihelion. They were also clustered in another orbital parameter called the longitude of perihelion, which combines the argument of perihelion with another angle describing the orientation of the orbital plane. When Bataille and Brown calculated the probability that 6 objects would show this degree of clustering by chance, they arrived at a figure of about 0.007, or roughly 0.7%. In statistical terms, this is just below the threshold scientists often use to claim a meaningful result, which is 1% or lower. It wasn't definitive proof, but it was compelling enough to take seriously. Bataille and Brown also identified another peculiarity. The 6 TNOs had orbital planes that were tilted in a similar way. When projected onto the plane of the solar system, their orbits formed a pattern that looked highly organized rather than random. Computer simulations showed that if you started with randomly oriented TNOs and let them evolve under the influence of a distant massive planet, they would naturally settle into this kind of configuration over hundreds of millions of years. The planet's gravity would act like a cosmic shepherd, nudging objects into similar orbits while leaving closer objects like Neptune and the classical Kuiper belt largely unaffected. This wasn't just a case of cherry-picking data to fit a desired conclusion. Bataille and Brown tested their hypothesis rigorously. They ran simulations without a 9th planet to see if the clustering could arise through other means, and it didn't. They tested whether observational bias could create the appearance of clustering if astronomers were only finding TNOs in certain parts of the sky. And while bias played a role, it couldn't fully explain the pattern. They even tested whether Neptune alone could produce the clustering through a phenomenon called resonance locking. And again, the answer was no. Every alternative explanation fell short. Only a distant, massive planet consistently reproduced what they were seeing. But extraordinary claims require extraordinary evidence, and the reaction from the astronomical community was mixed. Some researchers immediately embraced the Planet 9 hypothesis and began searching for it. Others were more cautious, pointing out that 6 objects was a very small sample, size, and that subtle biases in how and when those objects were discovered could skew the statistics. And then there were those who were downright skeptical. After all, this was Mike Brown we were talking about, the man who killed Pluto. In 2005, Brown and his team discovered Eris, a TNO slightly smaller than Pluto but more massive. That discovery triggered a crisis in planetary classification, because if Pluto was a planet, then so was Eris, and so were dozens of other large TNOs that would inevitably be found. Rather than expand the number of planets indefinitely, the International Astronomical Union voted in 2006 to reclassify Pluto as a dwarf planet, a decision that remains controversial to this day. Brown became both famous and infamous for his role in Pluto's demotion. He even wrote a book titled How I Killed Pluto and Why It Had It Coming. So, when Brown announced that he'd found evidence for a new ninth planet, the irony was not lost on anyone. Some critics joked that Brown was trying to atone for Pluto by giving us a replacement. Others questioned whether he was too eager to believe in Planet 9 because it would validate his legacy. Brown himself acknowledged the irony, but he insisted that the evidence spoke for itself. He wasn't trying to replace Pluto out of guilt. He was following the data, and the data pointed to something big lurking in the outer darkness. So, what exactly are we looking for? If Planet 9 exists, what would it actually look like? Based on Badigan and Brown's calculations, Planet 9 would have a mass somewhere between 5 and 10 Earth masses. For comparison, Earth has a mass of about 6 trillion kilograms, so Planet 9 would weigh 30 to 60 trillion kilograms. That makes it substantially more massive than Earth, but much smaller than the ice giants Uranus and Neptune, which are 14 and 17 Earth masses respectively. In terms of size, Planet 9 would probably have a radius about 2 to 4 times that of Earth, depending on its composition. If it's mostly rock and ice, it would be on the smaller end. If it has a thick hydrogen and helium atmosphere like a mini Neptune, it would be larger. Either way, it's not a gas giant like Jupiter or Saturn. It's more like a super-Earth or sub-Neptune, the most common type of planet found around other stars, but conspicuously absent from our own solar system. At least, absent from the inner solar system. At a distance of 400 to 800 astronomical units, Planet 9 would be unimaginably cold. The sun's warmth is negligible out there. Any heat the planet retains would come from its own interior, left over from its formation billions of years ago. Badigan and Brown estimate a surface temperature, or rather a cloud top temperature if it has an atmosphere, of around 40 Kelvin. That's negative 233 degrees Celsius, or negative 387 degrees Fahrenheit. For reference, liquid, nitrogen boils at 77 Kelvin, so Planet 9 would be cold enough to freeze nitrogen solid. This extreme cold means Planet 9 would emit almost no visible light of its own. It would only be visible through reflected sunlight, and even then, incredibly faintly. At 400 astronomical units, the Sun appears about 160,000 times dimmer than it does from Earth. Planet 9 would be a dark, frozen world illuminated by a sun that looks like just another bright star in the sky. Astronomers measure brightness using a logarithmic scale called apparent magnitude. The lower the number, the brighter the object. The brightest stars in the night sky have magnitudes around 0 or 1. The faintest stars visible to the naked eye are around magnitude 6. The faintest objects detectable by the Hubble Space Telescope are around magnitude 31. Badigan and Brown estimate that Planet 9 would have an apparent magnitude somewhere between 22 and 24, depending on its exact distance and size. That makes it about 16 million times fainter than the faintest stars you can see without a telescope. It's detectable, but only barely, and only with large professional telescopes equipped with sensitive cameras. And here's the real challenge. Planet 9 isn't just faint, it's also moving incredibly slowly. At 400 astronomical units, it would take Planet 9 roughly 10,000 years to complete one orbit. That means it moves across the sky at an agonizingly slow pace, covering only a few arc seconds per year. For comparison, the Moon moves about half a degree per hour. Planet 9 moves about 1/1000th of a degree per year. If you took a picture of a patch of sky tonight and another picture of the same patch a week later, Planet 9 would appear in almost exactly the same spot. You might mistake it for a distant background star or galaxy. To confirm it's moving, you'd need to observe it over months or even years. This is why Planet 9 could have been photographed multiple times already without anyone realizing it. Sky surveys take images of huge portions of the sky, but those images are primarily used to study distant galaxies and supernovae, not slow-moving solar system objects. Unless someone specifically looks for objects that move very slightly between images taken months apart, Planet 9 could be hiding in plain sight, buried in archival data. So, how do you actually search for something like this? The first step is to narrow down where to look. Battigan and Brown's simulations predict that Planet 9 is currently somewhere near aphelion, the farthest point in its orbit, which places it roughly 600 to 800 astronomical units from the Sun. They also predict that it's somewhere near the constellation Orion, based on the orbital alignments of the TNOs. But this is still an enormous search area, covering hundreds of square degrees of sky. For perspective, the full moon covers about half a square degree, so we're talking about searching an area equivalent to hundreds of full moons. And remember, Planet 9 is moving slowly, so you can't just take one picture and call it done. You need multiple observations over time to detect motion. Shortly after Battigan and Brown's paper was published, astronomers around the world began organizing search campaigns. The Subaru telescope in Hawaii, which has a wide field of view and sensitive camera, started scanning the predicted region. Other facilities, like the Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, also joined the hunt. Even amateur astronomers got involved, scouring publicly available sky survey data for anything unusual. But as weeks turned into months and months turned into years, no one found Planet 9. The searches ruled out large portions of the predicted orbital zone, gradually narrowing the parameter space where the planet could hide. Each negative result refined the predictions, pushing Planet 9 into smaller and smaller regions of sky. And yet, the lack of detection didn't necessarily mean Planet 9 wasn't there. It could simply be in a part of the sky that hasn't been searched thoroughly yet, or it could be fainter than expected, or slightly farther away, or obscured by the dense star fields of the Milky Way. The hunt continues. The search for Planet 9 has been punctuated by moments of excitement that evaporated into disappointment with frustrating regularity. In the years since Battigan and Brown published their prediction, there have been numerous occasions when astronomers thought they might have found it, only to realize they were chasing shadows. The first major false alarm came just months after the original paper. In the summer of 2016, a team of researchers led by Chris Lintott analyzed data from the Wide Field Infrared Survey Explorer, known as WISE, a space telescope that had surveyed the entire sky in infrared wavelengths between 2010 and 2011. Infrared is particularly useful for finding cold objects, because even though they don't emit much visible light, they still radiate heat. If Planet 9 existed and had any residual warmth from its formation, WISE should have been able to detect it. The team ran the numbers and came to an intriguing conclusion. WISE data seemed to rule out Planet 9 at distances greater than about 800 astronomical units, but it couldn't rule out a closer orbit. In fact, the data suggested that if Planet 9 existed, it might be closer to 400 astronomical units and slightly warmer than Battigan and Brown had predicted. This would make it brighter and easier to find. For a brief moment, it seemed like the search area had been dramatically narrowed. But there was a problem. The WISE analysis relied on assumptions about Planet 9's temperature and reflectivity, and small changes in those assumptions produced wildly different results. If Planet 9 was slightly colder or less reflective than expected, it could still be beyond WISE's detection threshold even at closer distances. The supposed constraint wasn't as constraining as it first appeared. Within months, other researchers poked holes in the analysis, and the excitement faded. WISE hadn't found Planet 9, and it hadn't definitively ruled out any particular region either. The search area remained frustratingly large. Then, in June 2017, a new paper appeared that complicated the picture even further. Astronomers Kat Volk and Renu Malhotra from the University of Arizona noticed something odd about the orbits of Kuiper Belt objects. Not the extreme distant TNOs that Battigan and Brown had focused on, but the more ordinary objects in the classical Kuiper Belt between 30 and 50 astronomical units from the Sun. These objects, Volk and Malhotra argued, showed a subtle warp in their orbital planes. Instead of being perfectly aligned with the invariable plane of the solar system, which is defined by the combined angular momentum of all the planets, the Kuiper Belt objects were tilted by about 8 degrees. This might not sound like much, but it was statistically significant. The odds of this warp occurring by chance were low, and the known planets couldn't explain it. Volk and Malhotra suggested that a different planet, perhaps smaller and closer than Planet 9, could be responsible. They dubbed it Planet 10, though the name was somewhat tongue-in-cheek. Their calculations suggested a Mars-sized object orbiting at around 60 astronomical units, far closer than Planet 9's predicted orbit. The media ran with the story, and for a few weeks, it seemed like the outer solar system was becoming crowded with hypothetical planets. But the Planet 10 hypothesis faced immediate skepticism. For one thing, an object at 60 astronomical units should be much easier to find than something at 600 astronomical units, and yet no such object had been detected despite thorough surveys of that region. For another, the statistical significance of the Kuiper Belt warp was marginal. With a larger sample of objects, the warp might disappear entirely, revealed as nothing more than noise. Within a year, follow-up studies cast serious doubt on the Planet 10 idea, and it quietly faded from serious consideration. But the episode highlighted a recurring problem in the Planet 9 search. Every new analysis seemed to suggest a different location, a different mass, a different orbit. Was this the natural process of science refining its predictions, or was it a sign that researchers were grasping at straws, seeing planets in every statistical anomaly? In 2019, yet another study claimed to have pinpointed Planet 9's location. Astronomers Matthew Holman and Matthew Payne used a different approach, analyzing the trajectories of long-period comets that occasionally swing through the inner solar system. These comets originate in the Oort cloud, the vast sphere of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units. If Planet 9 existed, its gravity should influence the orbits of these comets, biasing them toward certain directions. Holman and Payne found such a bias and calculated that Planet 9 was most likely located in a specific region of sky near the constellation Cetus. The prediction was precise enough that targeted searches could focus on a relatively small area. Several observatories added Cetus to their search lists. Months passed. Nothing was found. Either the prediction was wrong, or Planet 9 was even fainter than expected, or it simply wasn't there. Amateur astronomers also got involved, convinced they could succeed where professionals had failed. The advantage of amateur searches is sheer numbers. There are thousands of amateur astronomers around the world with access to decent telescopes and image processing software, and they're not constrained by the bureaucratic red tape that limits professional observations. Several amateurs claimed to have found Planet 9 in archival data, posting their findings on forums and social media. Each claim generated brief excitement before being debunked. In most cases, the supposed detection turned out to be a distant galaxy, an asteroid, or a quirk of image processing. In one particularly embarrassing incident, an amateur claimed to have found Planet 9 based on an infrared signature in WISE data, only for professional astronomers to point out that the signature was caused by a known artifact in the telescope's detector. The emotional roller coaster of false alarms and near misses took a toll on the researchers involved. Badigan and Brown continued to express confidence that Planet 9 existed, but even they admitted frustration at the slow pace of the search. Every few months, a new paper would appear claiming to have narrowed down the location or refined the orbital parameters, and every few months, searches of that region would come up empty. It was like playing an infuriating game of cosmic whack-a-mole. So why is Planet 9 so difficult to find? Part of the answer lies in its intrinsic faintness, but that's only the beginning. The real challenge is the environment in which astronomers have to search. Planet 9's predicted location places it somewhere near the plane of the Milky Way galaxy, and that's a problem. When you point a telescope toward the galactic plane, you're looking through the densest concentration of stars in the sky. Millions of stars, along with countless distant galaxies, crowd into the field of view. Planet 9 would appear as an incredibly faint dot among a sea of brighter dots, and distinguishing it from background stars requires careful analysis. You need multiple observations over time to detect its slow motion, but coordinating those observations is easier said than done. Ground-based telescopes face additional challenges. Earth's atmosphere is constantly in motion, turbulent and swirling, which blurs and distorts the light from distant objects. This is why stars appear to twinkle. For faint objects like Planet 9, atmospheric distortion can make the difference between detection and invisibility. Adaptive optics systems can compensate for some of this distortion by rapidly adjusting the shape of the telescope's mirror, but they're not perfect, especially for wide-field surveys that need to cover large areas of sky. Weather is another obstacle. Observatories are located in remote locations with clear skies and low light pollution, but even the best sites experience clouds, storms, and other conditions that shut down observations for nights or weeks at a time. When you're searching for an object that requires multiple observations spaced months apart, every lost night is a setback. And then there's the issue of telescope time. Professional observatories are in high demand. Astronomers from around the world submit proposals for observation time, and competition is fierce. A typical large telescope might receive 10 times more proposals than it can accommodate, which means the vast majority are rejected. Proposals are ranked based on scientific merit, feasibility, and potential impact, and Planet 9 searches have to compete with studies of distant galaxies, exoplanets, supernovae, and countless other projects. Even if a Planet 9 proposal is accepted, the allocated time might be just a few nights per year. nowhere near enough to systematically search the entire predicted region. Badigan, Brown, and their collaborators have had to piece together observations from multiple telescopes over multiple years, stitching together a patchwork of data that's far from comprehensive. Some regions of sky have been observed dozens of times. Others have never been observed at all. The uneven coverage makes it difficult to draw firm conclusions. Just because Planet 9 hasn't been found yet doesn't mean it's not there. It could easily be hiding in one of the many gaps in the search. Despite these challenges, the search has produced a steady stream of new trans-Neptunian object discoveries, and many of them have only strengthened the case for Planet 9. In 2016, shortly after Badigan and Brown's paper was published, astronomers discovered an object designated 2015 RR245. It was found in data from the Outer Solar System Origins Survey, known as OSSOS, a systematic survey designed to find and characterize TNOs. RR245 has a semi-major axis of about 82 astronomical units and an orbital period of roughly 700 years. While not as extreme as Sedna or the objects Badigan and Brown focused on, RR245 added to the growing population of distant TNOs. Its orbit showed some degree of clustering with the others, though the statistical significance was still debated. Then, in October 2018, came a discovery that genuinely excited Planet 9 proponents. Scott Shepard, Chad Trujillo, and David Tholen announced the discovery of 2015 TG387, an object they nicknamed the Goblin because it was first observed near Halloween. The Goblin is one of the most extreme objects ever found. Its perihelion is about 65 astronomical units, far beyond Neptune's influence, and its semi-major axis is over 1,100 astronomical units. Its orbital period is roughly 40,000 years. At aphelion, the Goblin travels out to more than 2,100 astronomical units, well into the inner Oort cloud. What made the Goblin particularly interesting was its argument of perihelion. Like the other extreme TNOs, it fit the clustering pattern that Badigan and Brown had identified. Its orbit was aligned in just the way Planet 9's gravity would predict. Shepard and his team ran simulations and found that the Goblin's orbit remained stable over billions of years, only if a massive, distant planet was present. Without Planet 9, the Goblin should have been scattered into a different orbit long ago by interactions with the known planets or passing stars. The discovery of the Goblin brought the total number of clustered extreme TNOs to around 10, depending on how you defined the selection criteria. With each new addition, the statistical improbability of the clustering grew. Badigan and Brown recalculated the odds and found that the probability of such clustering occurring by chance had dropped to something like 1 in 500. Then, in 2019, astronomers discovered an object even more distant than the Goblin. It was designated 2018 AG37 and given the nickname Far Far Out, a play on the earlier discoveries Far Out and Far Far Out. At the time of discovery, Far Far Out was about 140 astronomical units from the Sun, making it the most distant solar system object ever observed. Its orbit takes it out to approximately 175 astronomical units at aphelion, and it has an orbital period of roughly 1,000 years. Far Far Out's orbit is less extreme than the Goblin's, and its alignment with the clustering pattern is less clear, but its sheer distance made it another data point in the ongoing mystery of the outer solar system. Not every new discovery supported the Planet 9 hypothesis. Some TNOs had orbits that didn't fit the predicted pattern, and a few seemed to contradict it outright. Critics pointed to these outliers as evidence that the clustering was not as robust as Planet 9 proponents claimed. But Batygin and Brown argued that outliers were expected. Planet 9's influence wouldn't affect every TNO equally. Some would be sculpted into aligned orbits, while others would be scattered into random trajectories. The key was whether the overall population showed statistically significant clustering, and by their reckoning, it did. As more objects were discovered, Batygin and Brown continued to refine their simulations. The original 2016 paper was just the beginning. In the years since, they and other researchers have run increasingly sophisticated models to test the Planet 9 hypothesis under different conditions. These simulations rely on solving what's known as the N-body problem, one of the oldest and most challenging puzzles in celestial mechanics. The N-body problem asks a deceptively simple question. If you have N objects, each pulling on all the others through gravity, how will their orbits evolve over time? For two objects, like the Earth and the Moon, the problem has an exact analytical solution. But for three or more objects, there's no general solution. You have to use numerical methods, essentially letting a computer calculate the positions and velocities of all the objects in tiny time steps, over and over again, until you've simulated millions or billions of years of orbital evolution. For Planet 9 simulations, N is very large. You need to include the Sun, the 8 known planets, dozens of TNOs, and Planet 9 itself. Each simulation runs for billions of virtual years to see how the TNO's orbits change under Planet 9's influence. The computational cost is enormous, requiring weeks or months of processing time on powerful computers. In 2019, Batygin and Brown published an updated analysis based on more refined simulations. They tightened the constraints on Planet 9's mass and orbit, suggesting it was most likely around 6 Earth masses, with a semi-major axis of about 460 astronomical units and an eccentricity of around 0.2 to 0.5. The new parameters shifted the predicted location slightly, concentrating the search area in a different part of the sky. The updated predictions also suggested that Planet 9's orbit was more circular than originally thought, which meant it stayed farther from the Sun on average, making it even fainter. In 2021, another study by Michael Brown and Konstantin Batygin pushed the analysis further, incorporating additional TNO discoveries and testing whether alternative explanations could account for the clustering. They concluded that the clustering remained statistically significant and that Planet 9 was still the most likely explanation. However, they also acknowledged that observational biases complicated the picture, a point we'll return to shortly. One of the most intriguing pieces of evidence for Planet 9 has nothing to do with TNOs. It concerns the solar system itself. If you measure the orbital planes of the 8 known planets, you'll find they're all tilted by about 6 degrees relative to the Sun's equator. This might not seem like much, but it's actually quite strange. Planets form from a rotating disk of gas and dust around a young star, and that disk should be aligned with the star's rotation. So why is the solar system's orbital plane tilted? For decades, astronomers assumed the tilt was caused by some event early in the solar system's history, perhaps a close encounter with another star or asymmetries in the protoplanetary disk. But no one had a satisfying explanation. In 2016, just a few months after the original Planet 9 paper, Batygin published a follow-up study showing that Planet 9 could explain the tilt. If Planet 9 exists and has the predicted mass and orbit, Its gravitational influence over billions of years would gradually torque the orbits of the inner planets, tilting them relative to the Sun's equator. The effect is subtle and accumulates over eons, but the math worked out. A 6-degree tilt was exactly what you'd expect from a planet like Planet 9. For proponents of the hypothesis, this was stunning confirmation. Planet 9 didn't just explain the clustering of TNOs, it also explained a long-standing mystery about the solar system's architecture. It was a unifying theory that tied together multiple lines of evidence. For skeptics, it was suspicious. They argued that Badigan was retrofitting the theory to match the data. After all, the tilt of the solar system's orbital plane was a known fact before Planet 9 was proposed. Was it really evidence for the planet, or was Badigan cherry-picking phenomena that happened to fit his model? The debate remains unresolved, but it highlights the challenge of distinguishing between genuine predictions and post hoc rationalizations. Despite years of searching, Planet 9 remains elusive, and it's worth asking where we've already looked. Multiple surveys have scanned large portions of the sky in search of faint, slow-moving objects. The Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, has surveyed most of the northern sky multiple times. The Dark Energy Survey, originally designed to study distant galaxies, has covered much of the southern sky. The Outer Solar System Origins Survey focused specifically on the region beyond Neptune. When you combine the coverage from all these surveys, roughly 60 to 70% of Planet 9's predicted orbital zone has been searched to some degree. And yet, nothing has been found. So, what does that mean? There are 3 possibilities. First, Planet 9 is in the unsearched 30 to 40%. This is entirely plausible. The unsearched regions include parts of the sky near the galactic plane where the density of background stars makes searches particularly difficult. If Planet 9 happens to be in one of those regions, it could remain hidden for years until better surveys come online. Second, the predictions are slightly wrong. Maybe Planet 9 is a bit farther away or a bit fainter than expected, placing it just beyond the detection threshold of current surveys. Small adjustments to its mass, orbit, or reflectivity could make it invisible to existing telescopes while still producing the observed clustering of TNOs. Third, Planet 9 doesn't exist. This is the null hypothesis, the possibility that the clustering is a statistical fluke or caused by something other than a planet. It's a possibility that even Badigan and Brown acknowledge, though they consider it unlikely. Each new survey that comes up empty shifts the probabilities slightly, but it doesn't rule out the planet entirely. It just constrains where and what it could be. And this brings us to the most contentious issue in the Planet 9 debate, the problem of observational bias. Critics of the Planet 9 hypothesis argue that the clustering of TNOs might not be real. Instead, it could be an artifact of how and when astronomers search for these objects. Here's the problem. Finding TNOs is hard, and astronomers don't search the sky randomly. They focus on regions where they're most likely to succeed, and those regions are determined by practical considerations like telescope availability, sky brightness, and the position of the moon. Most TNO surveys are conducted when the moon is new or nearly new to minimize its light pollution. They also tend to focus on regions of sky that are high above the horizon, where atmospheric distortion is minimized. These constraints mean that certain parts of the sky are observed far more often than others. If Planet 9's orbit happens to be oriented such that the TNOs it influences are easiest to find during these biased observations, the clustering could be an illusion. We're not finding TNOs everywhere they exist. We're finding them where we're looking, and we're looking in places that make them easiest to find. Several studies have tried to quantify this bias, and the results are mixed. Some find that bias can't fully explain the clustering, while others argue it can. A 2019 study by Kevin Napier, Larissa Marquardt, and colleagues analyzed the orbits of TNOs discovered by OSOS, a survey specifically designed to minimize observational bias. They found that when you account for where and when OSOS observed the sky, the clustering of TNOs becomes much less significant. In fact, the OSOS data alone didn't show strong evidence for clustering at all. Badigian and Brown pushed back, arguing that the OSOS sample was too small, and that when you combine it with discoveries from other surveys, the clustering remains robust. But the criticism stung, and it highlighted a fundamental problem. Until we have a truly unbiased survey that covers the entire sky uniformly, we can't definitively say whether the clustering is real or an artifact. The debate over observational bias resembles the age-old question of whether we see patterns in noise. Humans are exceptionally good at finding patterns, even when none exist. We see faces in clouds, constellations in stars, and meaning in randomness. Are we doing the same with Planet 9, projecting order onto chaos because we want to believe there's something out there? Or is the pattern real and the skeptics are simply being overly cautious? The answer will likely come down to one thing: finding the planet. Until Planet 9 is actually detected, or until surveys definitively rule it out, the debate will continue. And with every year that passes without a discovery, the tension grows. In September 2019, two physicists named Jakob Scholz and James Unwin published a paper that took the Planet 9 hypothesis in a direction nobody saw coming. They agreed that something massive was lurking in the outer solar system, something with 5 to 10 Earth masses that was gravitationally shepherding distant trans-Neptunian objects into their peculiar orbits. But they suggested it might not be a planet at all. It might be a black hole. Not the kind of black hole formed from the collapse of a massive star, mind you. Those are huge, typically several times the mass of the Sun, and we'd definitely have noticed one of those in our cosmic backyard. No, Scholz and Unwin were talking about something called a primordial black hole, an object formed in the very early universe, mere fractions of a second after the Big Bang. And here's the kicker. A primordial black hole with 5 to 10 Earth masses would be about the size of a grapefruit. To understand why anyone would seriously propose such an outlandish idea, we need to talk about what primordial black holes actually are. In the first moments after the Big Bang, the universe was unimaginably dense and hot. Matter and energy were packed together so tightly that even tiny fluctuations in density could have caused certain regions to collapse under their own gravity, forming black holes. These weren't formed from stars because stars didn't exist yet. They were formed directly from the primordial soup of the early universe. The mass of a primordial black hole depends on when and how it formed, and theoretical models suggest they could range from microscopic, far smaller than an atom, to thousands of solar masses. Crucially, primordial black holes with masses between about 1/10 of Earth's mass and several hundred Earth masses are particularly interesting because they could solve one of the biggest mysteries in cosmology. They could be dark matter. Dark matter is the invisible substance that makes up about 85% of all matter in the universe. We know it exists because we can see its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the cosmos. but we have no idea what it's made of. Decades of experiments have searched for exotic particles like WIMPs and axions, and so far we've found nothing. Primordial black holes offer an alternative. If enough of them formed in the early universe, they could account for all the dark matter we observe without requiring any new particles or physics. They're just black holes, objects we already know exist, but formed under exotic conditions. So, when Schultz and Unwin proposed that Planet 9 might be a primordial black hole, they weren't just explaining the clustering of TNOs. They were potentially solving two mysteries at once. The advantage of the black hole hypothesis is that it produces exactly the same gravitational effects as a planet. Gravity doesn't care whether the mass is spread out in a rocky sphere or compressed into a microscopic singularity. A 5 Earth mass black hole would tug on distant TNOs in precisely the same way as a 5 Earth mass planet. All the simulations that Battigan and Brown ran to predict Planet 9's orbit would work equally well for a black hole. But there's a critical difference. A planet reflects sunlight, which makes it detectable, albeit faintly. A black hole, especially one as small as a primordial black hole, emits almost no light at all. It would be functionally invisible to conventional telescopes. This explains why we haven't found Planet 9 yet. We've been looking for reflected sunlight, but if it's a black hole, there's no sunlight to reflect. Now, before you dismiss this as pure science fiction, it's worth noting that the idea isn't as crazy as it sounds. Primordial black holes are a legitimate area of research in cosmology, and there's observational evidence that they might exist. In 2015, the LIGO experiment detected gravitational waves from merging black holes, and some of those black holes had unexpected masses. A few were in a range that's difficult to explain through standard stellar evolution, which led some physicists to speculate they might be primordial. Additionally, several astronomical observations have hinted at the presence of small black holes drifting through the galaxy. In 2020, a study analyzed microlensing events, where a massive object passing in front of a distant star temporarily brightens it due to gravitational lensing, and found evidence for a population of black holes with masses between a fraction of a solar mass and a few solar masses. These could be primordial black holes, or they could be the remnants of ancient stars, but the data is ambiguous. The primordial black hole hypothesis for Planet 9 is speculative, but it's not fringe nonsense. It's a testable idea grounded in known physics. The challenge is figuring out how to test it. If Planet 9 is a black hole rather than a planet, how would we find it? Schultz, Unwin, and other researchers have proposed several detection methods. The first and most straightforward is gravitational lensing. When a massive object passes in front of a background star, its gravity bends and magnifies the star's light, creating a temporary brightening event. For a 5 Earth mass black hole at 600 astronomical units, these events would be rare but detectable. The Vera Rubin Observatory, which is scheduled to begin operations in the mid-2020s, will conduct a systematic survey of the sky and should be able to detect micro-lensing events caused by a Planet 9-sized black hole. The challenge is that micro-lensing events are brief, lasting days to weeks, and you need to be looking at the right part of the sky at the right time. But Vera Rubin will observe huge portions of the sky every few nights, so the odds are good. Another detection method involves looking for annihilation signals. If dark, matter is made of particles rather than black holes. Those particles could accumulate around the black hole's event horizon due to its gravity. When matter and antimatter particles meet, they annihilate and produce gamma rays. If Planet 9 is a primordial black hole surrounded by a halo of dark matter particles, it might emit a faint but detectable gamma ray signal. The Fermi Gamma Ray Space Telescope has been scanning the sky for such signals for over a decade, and researchers have searched its archives for anomalies in the region where Planet 9 is predicted to be. So far, nothing conclusive has been found, but the absence of evidence isn't evidence of absence. The black hole might not have accumulated enough dark matter to produce a detectable signal, or the signal might be too faint for current instruments. In 2020, the renowned physicist Edward Witten proposed yet another method. Witten suggested that a primordial black hole in the outer solar system might occasionally capture and consume small pieces of debris, comets, asteroids, or other material drifting through interstellar space. When matter falls into a black hole, it heats up and emits X-rays just before crossing the event horizon. These accretion flares would be brief and sporadic, but if we monitored the predicted region with X-ray telescopes, we might catch one. Witten's proposal was elegant, but it relied on the black hole encountering enough material to produce detectable flares, which is far from guaranteed given the emptiness of the outer solar system. Then, in June 2020, a tantalizing anomaly emerged. The Xenon 1T detector, a highly sensitive instrument located deep underground in Italy and designed to search for dark matter particles, reported an unexpected excess of events. The detector had picked up more signals than could be explained by known background radiation. The excess was small, only slightly above the expected noise, but it was statistically significant. One possible explanation was that the detector had captured interactions with dark matter particles, potentially the same particles that might surround a primordial black hole like Planet 9. For a few months, excitement rippled through the physics community. Could this be the first direct evidence of dark matter, and could it somehow be connected to Planet 9? Unfortunately, follow-up analysis deflated the excitement. The excess events could be explained by trace amounts of tritium, a radioactive isotope of hydrogen, contaminating the detector. By early 2021, most physicists concluded that the Xenon 1T anomaly was probably not dark matter after all, just an instrumental quirk. But the episode illustrated how intertwined the search for Planet 9 has become with broader questions in physics. If Planet 9 is a primordial black hole, finding it would revolutionize our understanding of dark matter, black holes, and the early universe. Ironically, a black hole might actually be easier to find than a planet, at least in some respects. A planet can only be detected through reflected sunlight, which requires it to be bright enough and in a region of sky with relatively few background stars. A black hole, on the other hand, can be detected through gravitational lensing, gamma-ray emissions, or accretion flares, any of which could occur even if the black hole is in a crowded star field. The trade-off is that these signals are rare and require different instruments than those used to search for planets. While the primordial black hole hypothesis is exotic, there's an even more radical alternative, one that doesn't require finding any new object at all. Instead, it requires rewriting the laws of physics. In the early 1980s, physicist Mordechai Milgram proposed a modification to Newton's laws of gravity called MOND, which stands for Modified Newtonian Dynamics. Milgram was trying to explain a long-standing puzzle in astronomy. When you measure the rotation speeds of galaxies, the outer regions rotate much faster than they should based on the visible matter. the standard explanation is dark matter, an invisible mass that provides the extra gravity needed to hold galaxies together. But Milgram suggested an alternative. What if gravity itself behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies? Under Mond, Newton's inverse square law is tweaked so that gravity doesn't weaken as quickly at large distances. This modification can explain galactic rotation curves without invoking dark matter. Mond has its fans and its critics. It works well for some observations but struggles to explain others, like the distribution of mass in galaxy clusters. Most physicists favor dark matter over Mond, but the debate is far from settled. So what does this have to do with Planet 9? In 2020, astronomer Rory Barnes published a paper exploring whether Mond could explain the clustering of trans-Neptunian objects without requiring a ninth planet. The idea is that if gravity behaves differently at the extreme distances where these TNOs orbit, their trajectories might naturally cluster in ways that standard Newtonian gravity wouldn't predict. Barnes ran simulations incorporating Mond and found that the modification did produce some clustering, but not enough to fully match the observations. The clustering under Mond was weaker and less organized than what Badigian and Brown had reported. To make Mond work, you'd need to fine-tune the parameters in ways that felt artificial. Most researchers concluded that Mond couldn't explain Planet 9's effects, at least not in its current form. But the exercise was valuable because it highlighted how little we understand about gravity at the extreme edges of the solar system. If Planet 9 doesn't exist, and if the clustering is real, then something strange is going on, and modified gravity is one of the few alternatives left on the table. The problem with modified gravity theories is that they're incredibly radical. If Mond, or something like it, is correct, we'd have to rewrite huge swaths of physics. Newton's laws and Einstein's general relativity have been tested exhaustively, and they work extraordinarily well in virtually every context. Abandoning them to explain a handful of TNOs feels like overkill. It's using a sledgehammer to crack a nut. But science has been upended by seemingly small anomalies before, so we can't dismiss the possibility entirely. A less radical alternative was proposed in 2019 by astronomers Antranik Sefilian and Jihad Touma. They suggested that the clustering of TNOs might not be caused by a single massive planet or black hole, but by a massive disk of icy debris in the outer solar system. The idea is that if there's enough mass distributed across a large disk beyond Neptune, the collective gravity of all that material could mimic the effects of Planet 9. Sefilian and Touma ran simulations and found that a disk with a total mass of several Earth masses spread out over a region from 100 to 500 astronomical units could produce the observed clustering. The disk would be composed of countless small objects, each individually undetectable, but together adding up to significant gravitational influence. This hypothesis has some appeal because it doesn't require finding a single elusive object. Instead of one needle in a haystack, we're talking about the entire haystack acting like a needle. But it also has significant problems. For one thing, we haven't detected this massive disk either. If it exists, it should contain thousands or even millions of TNOs, many of which should be large enough to detect with current surveys. The fact that we haven't found them suggests either the disk doesn't exist, or its mass is much lower than required. For another, the simulations are sensitive to the disk's exact properties. Change the mass distribution, the eccentricity of the orbits, or the inclination of the disk, and the clustering either disappears or changes in ways that don't match observations. Cephalian and Tuma's model works, but only if you dial in the parameters very precisely, which feels suspiciously like fine-tuning. Most astronomers view the self-gravitating disk hypothesis as less satisfying than Planet 9 because it trades one unseen object for a whole population of unseen objects. It doesn't simplify the problem, it complicates it. Then there's the capture hypothesis, an idea that takes Planet 9's story in yet another direction. In 2020, astronomers Alexander Mustel, Sean Raymond, and Melvin Davies proposed that Planet 9 might not have formed in our solar system at all. Instead, it could be an exoplanet, a planet that originally formed around another star and was later stolen by the Sun during a close encounter. This might sound far-fetched, but it's actually quite plausible given what we know about the Sun's early history. Stars don't form in isolation. They form in clusters, dense groups of hundreds or thousands of young stars packed into a relatively small volume of space. The Sun was born in such a cluster about 4.5 billion years ago, and for the first few million years of its life, it was surrounded by neighboring stars separated by distances of just a few thousand astronomical units. In such a crowded environment, close encounters between stars would have been common. If the Sun passed within a few hundred astronomical units of another star, the gravitational interaction could have stripped a planet from that star's outer regions and transferred it into orbit around the Sun. Mustel and his colleagues ran simulations and found that the capture probability was low, but not negligible. For every few hundred close encounters, you might expect one successful planet capture. Given the number of stars in the Sun's birth cluster, it's plausible that the Sun captured at least one planet. The capture hypothesis has a major advantage. It naturally explains Planet 9's weird orbit. If Planet 9 formed in our solar system, it's hard to understand how it ended up on such an eccentric, tilted orbit so far from the Sun. Scattering by Jupiter and Saturn could explain part of it, but the details are tricky. If Planet 9 was captured from another star, though, its orbit would be expected to be strange. It would retain some of the orbital characteristics of its original system, modified by the capture event. Studying Planet 9 would then be like studying a piece of another planetary system, a planet that formed under different conditions around a different star. This has profound implications for planetary science. If we could determine Planet 9's composition, atmosphere, and internal structure, we'd gain insights into planet formation processes in other stellar systems. It would be the closest exoplanet we'd ever study, even if it's technically part of our solar system now. Of course, all of this assumes Planet 9 exists in the first place, which brings us to the skeptics, the astronomers who think the entire Planet 9 hypothesis is built on shaky statistical foundations and wishful thinking. The most vocal critics argue that the clustering of trans-Neptunian objects isn't real. It's an artifact of observational bias, the result of astronomers finding objects where and when they happen to look, rather than a genuine physical phenomenon. We've already discussed this issue in the previous section, but it's worth reiterating because it represents the null hypothesis, the possibility that there's nothing unusual going on at all. Critics like Kevin Napier and his colleagues have pointed out that when you carefully account for the observational biases in TNO surveys, the statistical significance of the clustering drops dramatically. In some analyses, the clustering disappears entirely, reduced to noise. They argue that proponents of Planet 9 are engaging in what's known as p-hacking, the practice of tweaking your analysis until you get a statistically significant result, even if that result is meaningless. Napier's team has also noted that the more TNOs we discover, the weaker the clustering appears. Early studies with 6 or 7 objects showed strong alignment. But as the sample size has grown to 15 or 20 objects, some of the new discoveries don't fit the pattern as neatly. This is the opposite of what you'd expect if Planet 9 were real. More data should strengthen the case, not weaken it. Another criticism is that Planet 9 is unfalsifiable, at least in its current form. Every time a search comes up empty, proponents adjust the parameters. Planet 9 is a bit farther away, a bit fainter, in a slightly different part of the sky. The hypothesis is flexible enough to accommodate almost any negative result, which makes it difficult to disprove. This is a red flag in science. A good hypothesis should make specific, testable predictions that can be proven wrong. There's also the psychological factor. Humans love finding patterns, even when none exist. We see faces in clouds, animals in constellations, and meaning in random noise. The history of astronomy is littered with examples of astronomers convincing themselves they'd found something that wasn't there, from the canals of Mars to the planet Vulcan orbiting inside Mercury's orbit. Both turned out to be illusions, caused by observational limitations and cognitive bias. Are we repeating that mistake with Planet 9? The skeptics say yes. They argue that the desire to discover a new planet, especially one that would elevate Planet 9 to legendary status, is clouding judgment. We want to believe there's something out there, so we're interpreting ambiguous data in the most exciting way possible. The null hypothesis, that the clustering is random and Planet 9 doesn't exist, is boring, but boring doesn't mean wrong. Science requires us to consider the possibility that we're chasing a ghost. So, where does that leave us? We have multiple competing explanations for the clustering of trans-Neptunian objects, assuming the clustering is even real. Let's compare them systematically. The Planet 9 hypothesis requires the existence of one object we haven't found yet. It's the simplest explanation in terms of the number of assumptions it makes. We know planets exist. We know they can have eccentric orbits. We know they can gravitationally influence other objects. All we have to do is find it. The downside is that we've been looking for years and haven't found it, which either means it's hiding in an unsearched region, or our predictions are slightly off, or it doesn't exist. The primordial black hole hypothesis requires more exotic physics, but has the advantage of explaining why we haven't found Planet 9 with optical telescopes. It also connects to the dark matter problem, potentially solving two mysteries at once. The downside is that we have no direct evidence for primordial, black holes in the mass range we need, and the detection methods are more speculative. Modified gravity theories like MOND are the most radical option. They require rewriting fundamental physics, which is a huge ask for explaining a handful of TNOs. The upside is that modified gravity could potentially solve other problems in cosmology, like galactic rotation curves, without invoking dark matter. The downside is that MOND doesn't currently fit the Planet 9 data very well, and most physicists are skeptical of modifying gravity without stronger evidence. The self-gravitating disk hypothesis doesn't require new physics, just a large population of undiscovered TNOs. The problem is, we haven't found that population either, and the hypothesis requires fine-tuning the disk's properties to match observations. It's not clear this is any simpler than just invoking Planet 9. The capture hypothesis is appealing because it explains Planet 9's weird orbit naturally, but it doesn't change the fundamental problem. We still need to find the planet, whether it formed here or was stolen from another star. And finally, the null hypothesis. Maybe there's no Planet 9, no primordial black hole, no modified gravity, no massive disk. Maybe the clustering is just noise, and we're seeing patterns where none exist. This is the most conservative option, but it's also the least satisfying because it leaves the observations unexplained. Applying Occam's razor, the principle that the simplest explanation is usually correct, Planet 9 seems like the best bet. It requires the fewest assumptions and fits the data reasonably well. But Occam's razor isn't foolproof. Sometimes the universe is genuinely weird, and the simplest explanation is wrong. Until we find Planet 9, or definitively rule it out, all of these alternatives remain on the table. And the clock is ticking. High in the Chilean Andes, on a mountain called Cerro Pachon, construction crews have spent the better part of 2 decades building what may be the most important telescope for the Planet 9 search. It's called the Vera C. Rubin Observatory, named after the astronomer who provided some of the strongest evidence for dark matter. And it's designed to do something no previous telescope has done: survey the entire visible sky, repeatedly, night after night, for 10 years straight. The heart of the Rubin Observatory is an 8.4-meter primary mirror, one of the largest telescope mirrors ever built. But what makes this telescope truly special isn't just its size, it's the camera. The Legacy Survey of Space and Time Camera, or LSST camera, is the largest digital camera ever constructed for astronomy. It has 3.2 billion pixels, roughly 400 times more resolution than a typical smartphone camera. Each image it captures covers an area of sky about 40 times the size of the full moon. To put that in perspective, if you printed one of these images at standard photograph resolution, it would be the size of a billboard. The camera is so sensitive, it could detect a candle flame on the moon. Starting in late 2025, the Rubin Observatory will begin its 10-year survey. Every few nights, it will image the entire southern sky, capturing everything from distant galaxies to asteroids in our own solar system. Over the course of a decade, it will generate something like 20 trillion bytes of data per night, creating the most comprehensive movie of the night sky ever made. For the Planet 9 search, this is a game changer. Remember, the challenge with finding Planet 9 isn't just that it's faint, it's that it moves incredibly slowly, and you need multiple observations spaced months or years apart to confirm that something is actually moving, and not just a background star or galaxy. The Rubin Observatory will provide exactly that. By comparing images of the same patch of sky taken weeks, months, or years apart, astronomers will be able to identify anything that's shifted position. Distant galaxies don't move. Stars barely move over human timescales. But objects in the solar system, even ones as far away as Planet 9, move measurably. The Rubin Observatory's systematic approach means it won't miss large regions of sky the way previous surveys have. It will cover everything visible from its location in Chile, which includes most of the regions where Planet 9 is predicted to be. If Planet 9 exists and has the properties Badigan and Brown predict, the Rubin Observatory should find it by the late 2020s. If it completes its survey without finding Planet 9, that will place incredibly tight constraints on where and what the planet could be. It won't definitively rule out Planet 9, nothing can, but it will force a major reevaluation of the hypothesis. Of course, the Rubin Observatory isn't just looking for Planet 9. Its primary mission is to study the structure and evolution of the universe, track near-Earth asteroids, observe supernovae and other transient events, and map the distribution of dark matter. Planet 9 is just one of many science goals, albeit one that generates a lot of public excitement. But the Rubin Observatory isn't the only hope. Other telescopes and surveys are also contributing to the search. The James Webb Space Telescope, launched in late 2021, has infrared capabilities that make it well-suited for detecting cold objects. Planet 9, if it exists, would emit a faint infrared glow due to its residual heat. Webb's sensitivity in the infrared could potentially detect Planet 9 even if it's too faint in visible light for ground-based telescopes. The challenge is that Webb has a relatively narrow field of view compared to survey telescopes like Rubin, so it can't scan large areas of sky quickly. It would need to know roughly where to look, which means it's better suited for follow-up observations once a candidate has been identified by a survey. There have also been proposals for a dedicated Planet 9 telescope, a small observatory designed specifically to search the predicted region with optimized instruments. Such a telescope wouldn't need to be enormous, just sensitive enough to detect magnitude 22 or 23 objects and equipped to track them over time. The cost would be relatively modest, tens of millions of dollars rather than billions, but securing funding for a single-purpose facility is challenging when competition for resources is fierce. As of now, no dedicated Planet 9 telescope has been funded, but the idea remains on the table. Then there's the role of citizen science. Projects like Backyard Worlds, Planet 9 invite members of the public to sift through telescope data looking for faint moving objects. The human eye is surprisingly good at spotting subtle patterns that automated algorithms sometimes miss, and with thousands of volunteers scanning the data, the odds of finding something increase. Backyard Worlds has already led to the discovery of dozens of brown dwarfs, objects that are too small to be stars but too large to be planets, drifting through the solar neighborhood. Some of these brown dwarfs are colder than Planet 9 would be, which proves that citizen scientists can find incredibly faint, slow-moving objects in archival data. If Planet 9 has been photographed by previous surveys but overlooked, Backyard Worlds volunteers might be the ones to spot it. The project has a dedicated Planet 9 search component, and while nothing has turned up yet, the search continues. So let's imagine the moment finally arrives. After years of searching, an astronomer notices something unusual in the latest batch of Rubin Observatory data. A faint dot that wasn't there 6 months ago. Or rather, it was there but in a slightly different position. The first step would be confirmation. You don't announce the discovery of a new planet based on a single observation. You need multiple images showing consistent movement in a direction and at a speed that matches what you'd expect for a distant object in the outer solar system. The astronomer would request follow-up observations from other telescopes to track the object's motion over weeks or months. If the object continues to move in the predicted way, excitement would build. But even then, caution would prevail. There have been too many false alarms over the years. The discovery wouldn't be announced publicly until the orbit had been calculated with reasonable precision. This could take months or even a year, depending on how much data is available. Once the orbit is confirmed, the next step would be to submit the findings to a peer-reviewed journal and notify the International Astronomical Union, the organization responsible for naming celestial objects. Here's a spoiler. It won't be called Planet 9. The IAU has strict naming conventions, and Planet 9 is an informal nickname used by astronomers and the media. If the object is confirmed to be a planet, it would eventually receive a formal name drawn from mythology, likely continuing the tradition of naming planets after Roman gods. Suggestions have ranged from Minerva to Vulcan to Persephone, though the final decision would rest with the IAU. The media circus would be immediate and overwhelming. The discovery of a new planet in our solar system would be front-page news around the world, dominating headlines for weeks. Battigan and Brown, assuming they're still leading the search, would become household names. There would be press conferences, interviews, documentaries, and endless speculation about what the planet looks like, whether it has moons, and what it means for our understanding of the solar system. But here's the reality check. Finding Planet 9 would only be the beginning. Refining its orbit to the precision needed to plan a mission would take years of additional observations. Even with the Rubin Observatory tracking it every few nights, calculating an orbit for an object that takes 10 to 20,000 years to go around the Sun is extraordinarily difficult. You're trying to determine the shape of an ellipse when you've only observed a tiny fraction of it. After the orbit is refined, the next question would be whether to send a mission, and the answer, almost certainly, would be yes. The discovery of Planet 9 would be one of the most significant astronomical findings in history, and the scientific community would push hard for a spacecraft to visit it. But launching a mission to Planet 9 would be a monumental challenge. Even at its closest approach to the Sun, Planet 9 would be hundreds of astronomical units away, and it's likely near aphelion right now, meaning it could be 600 or 700 astronomical units distant. For comparison, Voyager 1, the most distant spacecraft humanity has ever launched, is currently about 160 astronomical units from the Sun after traveling for over 4 decades. Reaching Planet 9 would require a spacecraft traveling significantly faster than Voyager, and even then, the journey would take decades. The most realistic approach would be something like New Horizons, but scaled up and faster. New Horizons, which flew past Pluto in 2015, was one of the fastest spacecraft ever launched. It left Earth at a speed of about 16 kilometers per second, received a gravity assist from Jupiter, and reached Pluto in 9.5 years. To reach Planet 9 in a reasonable time frame, say 30 to 40 years, a spacecraft would need to travel at roughly 20 to 30 kilometers per second. This is beyond the capabilities of conventional chemical rockets. You'd need advanced propulsion, likely nuclear. One option is a nuclear thermal rocket, where a nuclear reactor heats hydrogen propellant to extremely high temperatures, producing much more thrust than chemical rockets. Another option is nuclear electric propulsion, where a reactor generates electricity to power an ion drive. Both technologies have been studied for decades, but never fully developed for deep space missions. Launching such a mission would take time. First, you'd need funding, which means convincing governments or space agencies that the mission is worth the cost, likely several $billion. Then you'd need to design and build the spacecraft, which could take a decade or more. Then you'd need to wait for the right launch window, when the planets are aligned to provide optimal gravity assists. All told, even if Planet 9 is discovered tomorrow, a mission wouldn't launch until the 2040s at the earliest, and it wouldn't arrive until the 2070s or 80s. If we're unlucky with timing, we might not visit Planet 9 until the 22nd century. The mission itself would be a marvel of engineering. The spacecraft would need instruments to study Planet 9's size, mass, composition, and atmosphere, if it has one. It would carry cameras to photograph the planet and any moons it might have, spectrometers to analyze the chemical makeup of its surface or clouds, and magnetometers to detect a magnetic field. It would also need to survive decades in the harsh environment of deep space, withstanding radiation, micrometeorite impacts, and the cold of the outer solar system. The engineers and scientists who designed the mission would likely not live to see it arrive, a sobering reminder of the timescales involved in interstellar exploration. And yet, the mission would be worth it. Because Planet 9, if it exists, holds answers to some of the biggest questions in planetary science. How did the solar system form? How did the planets migrate to their current positions? How common are planets like Planet 9 around other stars? If Planet 9 is a captured exoplanet, it would be the first exoplanet we've ever studied up close, offering a window into the diversity of planetary systems in the galaxy. Even its composition would tell us a lot. Is it a rocky super-Earth, an icy world like Neptune, or something in between? Does it have an atmosphere? And if so, what's it made of? Does it have moons? And if so, how did they form? Every detail would refine our models of planet formation and evolution. And if Planet 9 turns out to be a primordial black hole, the implications would be even more profound. It would confirm that primordial black holes exist, that they can have planetary masses, and that at least some dark matter might be made of black holes rather than exotic particles. Studying it would require entirely new techniques, but the payoff would be a revolution in cosmology. Of course, there's another possibility. We don't find Planet 9. The Rubin Observatory completes its 10-year survey, scanning the entire southern sky hundreds of times, and comes up empty. Every predicted region is searched, every faint dot is tracked, and none of them turn out to be Planet 9. What then? The hypothesis wouldn't be dead, not entirely. Proponents could argue that Planet 9 is in a part of the sky not visible from Chile, or that it's fainter than expected, or that its orbit is different from the predictions. The parameter space would shrink, but it wouldn't disappear. However, a null result from the Rubin Observatory would be a major blow. It would mean that either Planet 9 doesn't exist, or it's so far outside the predicted parameters that we need to fundamentally rethink the hypothesis. At that point, alternative explanations would gain traction. The primordial black hole hypothesis would become more appealing because it explains why optical surveys haven't found anything. Modified gravity theories would get a second look. The self-gravitating disk hypothesis might be revisited with more sophisticated models. Or, most likely, astronomers would conclude that the clustering of trans-Neptunian objects is observational bias after all, and there's nothing unusual going on in the outer solar system. Science is full of negative results, hypotheses that seemed promising but turned out to be wrong. The planet Vulcan, proposed in the 19th century to explain anomalies in Mercury's orbit, never existed. The anomalies were real, but the explanation was general relativity, not a hidden planet. The canals of Mars, observed by astronomers in the late 19th and early 20th centuries, turned out to be optical illusions. Percival Lowell spent years searching for Planet X beyond Neptune, and while Clyde Tombaugh eventually found Pluto, Pluto was far too small to be the Planet X Lowell envisioned. If Planet 9 turns out to be a similar illusion, it would be disappointing, but it wouldn't be a failure. Science progresses by testing ideas and discarding the ones that don't hold up. The search for Planet 9 has already advanced our understanding of the outer solar system, spurring discoveries of new trans-Neptunian objects and refining our models of solar system dynamics. Even a null result would be valuable because it would tell us where Planet 9 isn't, narrowing the possibilities for future searches. There's something almost poetic about the Planet 9 search. We've mapped the surfaces of distant moons, detected planets around other stars, and peered billions of light years into the universe to study the earliest galaxies. And yet, we still don't know what's lurking in our own cosmic backyard. We've explored 99.999% of the solar system, but that last 0.001% could hold a Neptune-sized surprise. This isn't the first time humanity has searched for something hidden in the darkness. The hunt for Pluto took decades. Clyde Tombaugh spent months photographing the sky, comparing images by hand to spot the tiny dot that moved between frames. When he finally found Pluto in 1930, it was hailed as a triumph, the culmination of years of effort. But Pluto turned out to be much smaller and stranger than anyone expected, and it took another 75 years and a flyby by New Horizons before we truly understood what it was. The search for Vulcan, on the other hand, ended in disappointment. For decades, astronomers searched for a planet orbiting between Mercury and the Sun, convinced it had to exist to explain Mercury's orbital precession. They never found it because it didn't exist. The precession was eventually explained by Einstein's general relativity, a far more elegant solution than invoking a hidden planet. The canals of Mars, meanwhile, were a cautionary tale of seeing what we wanted to see. Astronomers like Percival Lowell convinced themselves that Mars was covered in artificial canals built by an advanced civilization. They published maps, wrote books, and gave lectures about Martian engineers. It wasn't until spacecraft visited Mars in the 1960s that the canals were revealed as illusions, tricks of light and shadow misinterpreted by observers eager to find signs of life. The Planet 9 search fits into this long tradition of humanity looking into the darkness and wondering what's out there. We're driven by curiosity, by the desire to solve puzzles, by the hope that we'll discover something that changes how we see the universe. Sometimes we succeed, sometimes we fail, but the search itself is worthwhile because it pushes the boundaries of what we know. As of late 2024 and early 2025, the search for Planet 9 is very much ongoing. The Vera Rubin Observatory is preparing for first light, with full survey operations expected to begin in mid-2025. Battigen and Brown continue to refine their predictions based on new trans-Neptunian object discoveries, and other research groups are running their own simulations to test alternative hypotheses. The most recent updates suggest that Planet 9, if it exists, is most likely near Aphelion, somewhere in the southern sky, possibly near the constellation Aries or Taurus. Its mass is probably around 5 to 7 Earth masses, and its current distance is estimated at 5 to 700 astronomical units. But these are educated guesses, not certainties. Every few months, a new trans-Neptunian object is discovered, and each one either strengthens or weakens the case for Planet 9. Some objects fit the clustering pattern beautifully. Others are outliers that don't fit at all. The statistical significance of the clustering remains hotly debated, with some studies claiming it's robust and others arguing it's marginal at best. There's an honesty to the current state of affairs. We don't know if Planet 9 exists. The evidence is tantalizing but not conclusive. The search has been going on for nearly a decade, and we're no closer to a definitive answer than we were in 2016. But we're also on the verge of a breakthrough. The Rubin Observatory, along with other next-generation telescopes and surveys, will provide the data needed to either find Planet 9 or rule it out. One way or another, we'll have an answer within the next 5 to 10 years, and that's what makes this moment so exciting. Most cosmic mysteries will remain unsolved for generations or centuries. We won't know the true nature of dark matter or dark energy in our lifetimes. We won't discover life on other planets anytime soon, if ever. We won't unravel the complete history of the universe or understand the deepest laws of physics. But Planet 9 is different. It's a mystery we can solve. It's a question that will be answered one way or another in the near future. If you're watching this documentary in 2025, there's a very good chance you'll live to see the day when Planet 9 is either found or definitively ruled out. You'll witness the culmination of a detective story that's been unfolding for nearly a decade. And if Planet 9 is found, you'll be alive during one of the most significant astronomical discoveries in history. A discovery that will rewrite textbooks, inspire a generation of scientists, and fundamentally change our understanding of the solar system. If it's not found, you'll witness the end of a fascinating hypothesis, a reminder that science is as much about what we don't find as what we do. Either outcome is meaningful. Either outcome advances our knowledge. The final chapter of the Planet 9 story is about to be written, and we're all here to see it. The solar system, vast and ancient, still holds secrets, and humanity, curious and persistent, refuses to stop searching. Whether Planet 9 is a hidden giant, a primordial black hole, or nothing more than a statistical ghost, the search itself is a testament to our desire to understand the universe we inhabit. We build telescopes to peer into the darkness. We run simulations to model worlds we've never seen. We spend years, decades, lifetimes chasing answers to questions that may not even have answers. And that, perhaps, is the most human thing we do. We look up at the night sky, at the vast expanse of space, and we ask, what's out there? The answer is coming. And it's coming soon.